Okay, let us look at another example. Let x be a uniform random variable in the interval 0, 1. Use the above result, that is the theorem, to derive the distribution of y, which is equal to negative log of x. Now, can we use the above theorem to get the distribution, that is cumulative distribution function or the density function? Uh, in this case, yes. Why? Because this transformation y is equal to negative log of x is actually a one-to-one transformation. So therefore, let us apply the theorem directly. So notice that y is equal to negative log of x is a one-to-one transformation from 0, 1 interval to 0 positive infinity interval. When x is equal to 0, y becomes positive infinity. When x is equal to 1, y becomes 0. Right? Hence the above result or the theorem can be applied because it's a one-to-one transformation. In addition to that, what do we need? We need to know the density function of x. Of course, the density function of x is equal to 1 in this case because x is in the uniform 0, 1 interval. So density function is just 1. In addition to that, we need the absolute value of the derivative of x with respect to y. So because y is equal to negative log of x is equal to e to the power negative y. So therefore the derivative of dx over dy is equal to negative e to the power negative y. What we need is the absolute value of that. Therefore the absolute derivative dx over dy is equal to e to the power negative y. So we can now directly apply the theorem. The density function of y evaluated at simple y is equal to the density function of x evaluated at x. Of course, that is equal to 1 because the density function is equal to 1. It doesn't depend on x in that case, times the absolute value of dx over dy, which is equal to the power y. So this is actually 1 times e to the power negative y when y is in 0 positive interval. So it is a familiar density function. Fy is equal to 1 times e to the power 1 times y when y is in the interval 0 infinity, and that is actually the density function of an exponential distribution with rate parameter 1. So therefore, we can say that y has an exponential distribution with rate parameter 1. Right? So not only we can derive the density function, we can also identify the name of the distribution in this case. So you can use it as a kind of a theorem if you want. If x is uniformly distribution between 0 and 1, then negative log of x has an exponential distribution with rate parameter 1. Okay, let's look at one more example here. This is a different situation. Suppose x has something called Pareto distribution, and its density function is given by this formula. I have made a mistake in typing mistake here. I want this capital X to be a subscript here, right? So f of subscript x evaluated at simple x is given by theta e to the power minus theta minus 1. Theta is a parameter, of course. And suppose we want to derive the distribution of y, which is equal to log of x. This problem is a little bit incomplete. I have to mention the set of the possible values of x here, right? I have not mentioned that. But here x is between x is from 1 to infinity. Right? This density function is defined from 1 to infinity. Uh, so then the log of x will be between 0 to infinity, right? From 0 to infinity, when x is equal to 1, log x is equal to 0, when x is equal to, when x goes to infinity, y goes to infinity. So we are looking at a one-to-one transformation from 1 infinity to 0 infinity interval. Hence, the theorem can be applied directly, right? So what we need is actually we need the derivative of x with respect to y, the absolute value of that. In addition to that, we need to find out uh, the density function of x evaluated at g inverse y, where g inverse y is equal to e to the power y. Right. So therefore, the density function of y evaluated at y is equal to f of x evaluated at g inverse y, that is evaluated at e to the power y, times the absolute derivative of x with respect to y. Right. So how do we get the density function evaluated at e to the power y? We have to substitute x equal to e to the power y in the density function of x. So the density function of x is given by this thing. So if you want to get the density function of, this is the density function of x evaluated at x. It is given by theta x to the power negative theta minus 1. So what we need is the density function of x evaluated at e to the power y. So in that case, we have to substitute e to the power y for this x here. Then we get this expression. And this is the derivative part, absolute derivative of x with respect to y. So when you simplify this, you get this expression, theta e to the power minus theta y. So the density function of y evaluated at simple y is equal to this expression. Here again, remember that y is between 0 and infinity, right? So you have to write down that domain of y to complete it as a density function. But again, notice that this is a well-known form of a density function. This is the density function of an exponential distribution with rate parameter theta. And the mean of that is actually 1 over theta, right? So therefore, again, there is a kind of a standard theorem, if you like. If x has a Pareto distribution with this density function in the interval 1 to infinity, then log of y has an exponential distribution with parameter theta. Right. Okay. Now, in these examples, we looked at situations, actually all those were one-to-one, but all those were either only monotonically increasing or monotonically decreasing. For example, this function is monotonically increasing. This transformation was monotonically decreasing. In this case, it was monotonically increasing, right? So all these examples were in one case always. But there are situations where we are interested in finding out the uh, distribution of a transformation, where the transformation is not uh, directly monotonic. It may contain one part which is monotonically increasing, part monotonically decreasing. In that kind of situations also, we can apply the theorem, but we have to apply those two in two different separate parts. Theorem cannot be applied directly when the transformation is non-monotonic. So as I mentioned, one thing we can do is we can apply the theorem when uh, the function behaves monotonically increasing, that part separately, and then the other parts separately. Or we can we can find out the cumulative distribution function using the definition of the cumulative distribution function, and then convert it into the, find the density function from that. So I'm going to show the second approach here for this example. find the cumulative distribution function and the density function of y is equal to x square, where x has a normal distribution with some mean mu and variance sigma square. So you know that when x has a normal distribution with mean mu and variance sigma square, x can be from minus infinity to plus infinity. So in that range, this function y is equal to x square is not directly monotonically increasing or monotonically decreasing. It is a curve, right? So we cannot directly apply. It's a curve. It's a curve with a minimum in this case because the coefficient is positive here. It's symmetric around some point, that is x equal to 0 point. So therefore, we cannot apply the theorem directly in this case. So we will see the second approach that I mentioned. We will find out the cumulative distribution function using the definition and then take the derivative of that to find out the density function. So let's consider any real number simple y. And then, well, first of all, yeah, we will consider the positive real number y. Fyy is equal to the probability x square less than or equal to y. You can say equal also here. But because this is a continuous random variable, it doesn't make a difference, right? I have forgotten to put the equal sign here. So in that case, this expression is equal to this one because remember, the random variable can take positive and negative values as well, right? So y we are considering is a positive value here, but then this expression is equivalent to the probability that x is between negative root y and positive root y. So that can be written as probability x less than this number minus the probability x less than this number. Now we can, if you want, you can actually write down another line by standardizing this thing. This is the same as probability x minus mu over sigma less than this number minus mu divided by sigma minus the probability x minus mu divided by sigma less than negative root y minus mu divided by sigma. That is, standardizing, right? So in that case, this becomes probability Z. Usually standardized normal random variable is denoted by Z. So you can write down probability Z less than root y minus mu over sigma minus the probability Z less than negative root y minus mu divided by sigma. So therefore, it's actually the cumulative distribution function of Z. Z is a standard normal random variable. Usually there's a standard notation for the cumulative distribution function of a standard normal random variable, which is denoted by capital Phi. Right? So this is the standard notation, special notation actually. Otherwise, we can write down capital F subscript x, that is also possible, but this is a special notation for the cumulative distribution function of a standard normal random variable. So here what we have here is then we can say that is the cumulative distribution function of Z evaluated at standardized value of this value minus the cumulative distribution function of Z evaluated at the standardized value of this. So that is the expression you can write down in general for the cumulative distribution function of y, where y is equal to x square. Now, if you want to get the density function, then we have to differentiate this function with respect to y. So when you differentiate this thing with respect to y, you get on the left-hand side, you get the density function of y evaluated at y. But when you differentiate this one with respect to y, you get the density function of z. So the density function of z, that is the standard normal distribution density function. That is denoted by simple pi. So what you get is the simple pi, that is the density function of standard normal evaluated at this value times the derivative of this function. You have to apply the chain rule. Derivative of this thing with respect to y will give this part. So that's why you have a product of two things. When you differentiate this one, you get first the density function of is a standard normal random variable evaluated at this value times the derivative of this one, then minus the derivative of this one will be again the density function of z evaluated at this value, that is this part. And then when you differentiate this part, you will get a negative sign. With that one, you will get a positive sign here. And this is the derivative of that, which with a derivative of this thing with respect to that, multiplied by the negative sign, that becomes plus t. Now, if you want, you can further simplify this, noticing that the density function of a standard normal distribution, that is denoted by the simple pi, is a symmetric distribution in this case. So therefore, uh, when you evaluate it as negative some z value, that is the same as evaluated at the positive z value. Therefore, this part here is the same as pi evaluated at the positive value of this. Positive value of this. That is positive root y plus y. So therefore, if you want, you can write down it as that part as this, and then the whole thing will be like this. So that's the density function of y. Of course, y has to be positive always. Therefore, there's no point of considering this simple y to be a negative value. When x is between negative infinity and positive infinity, y is always positive. It cannot be negative, positive or zero, of course, non-negative. So therefore, this y has to be a number greater than or equal to 0. So we are considering that kind of y here, y greater than or equal to 0. Right. So that is the easiest way to get the density function of y in this case. But if you want, as I mentioned, you could have obtained this part separately and this part separately and then add them up to get the full density function using the theorem. That was another approach that you could have used. Right. Now, we have looked at several examples. Let's look at another example where now we are interested in finding the expected value. And similarly, you might be interested in the variance also, but let's look at the expected value, how to find out the expected value of a transformed random variable. Right? How to find out the expected value of y, which is equal to gx. So again, you know already this thing. There are two ways you can do, two approaches. The first approach is, we have already discussed this thing earlier in our lessons. Directly, you can apply this thing gx times fx. So that will be expected value of g of capital X. Expected value of g of capital X is equal to integration of gx times the density with respect to x. That is the direct approach. Or the other approach is you find out first the density function of gx and then let's call it y, for example. So find out the density function of y and then use the usual definition of the expected value of y, that is integration of y times f of y dy. In that case, of course, you have to integrate from g of negative infinity to g of positive infinity according to the transformation. So limits, of course, you know this thing, limits have to be changed. But in that case, E of expected value of y will be equal to y times Fy of y dy. So that's where the previous theorem will be useful. You first find out the density function of y, which is equal to g of x, and then apply the usual definition of expected value of a single random variable. Right. Okay. Now we will look at a few more interesting results. This example explains you how to something called the probability integral transform. Probability integral transform. This is also very useful if you can consider it as a theorem, right? Let x be a continuous random variable with some CDF denoted by capital F subscript x. Right? So it's a known CDF, for example. Then, if we find out, we can find out the distribution of f of x evaluated at this random variable x. Let's call it y. So this is now a random variable. Now, there is a small thing that I want to explain here. Usually, we talk about f of x evaluated at some real number, simple x. So this whole thing is a real number in that case. But here we are looking at f of x evaluated at, with a random variable x. So therefore, this whole thing is a new random variable and we call it y. So if it's a random variable, it has some distribution density function and cumulative distribution function. So we are interested in finding out the density function of y here. Right? So actually, this is a very useful theorem. We can show that if x is a continuous random variable with some cumulative distribution function fx, then when we consider the new random variable fx, which is denoted by y, y will always have a uniform distribution in 0, 1 interval. That's a very interesting and useful result, as you will see later. So let's prove that theorem. It's actually, you can consider it as a theorem, even though I mentioned it as an example here. So y is equal to capital F subscript x evaluated at capital X. So let's find out the cumulative distribution function of y, first of all, at some real number y. So by definition, this is the probability y less than or equal to simple y, but we can now replace this y by f x less than or equal to y. Now, because fx is a non-decreasing function, it's a monotonically non-decreasing function, is going up always. So there is always a inverse for this fx. So therefore, we can write down this expression is equivalent to the probability x, this capital X, less than or equal to f inverse x evaluated at y. F inverse x exists always for a continuous random variable. And therefore, this now you can notice that this is the probability that x less than or equal to some value, real number here, right? Fx inverse is a function evaluated at this real number. This whole thing is a real number. So therefore, this thing is actually the cumulative distribution function of capital X evaluated at this value. So therefore, we can write down it as f of capital X evaluated at this value. So now you can see that you have fx and f inverse x. So that will give you f of x, f inverse xy is equal to y. So we have shown that the cumulative distribution function of y is y. And if you want, you can actually get the density function by taking the derivative of this thing with respect to y. That will give you 1. Now notice what are the values of this y can take in this case. In other words, what are the values that this random variable y can take? because y is equal to f of x, where f of x is equal to the probability that x less than or equal to something. The probability. The probability is always between 0 and 1. Yes, right? The probability is always between 0 and 1, inclusive those. Therefore, y is a random variable taking values between 0 and 1. Right? So we have the cumulative distribution function of y is equal to simple y. Y take values between 0 and 1. So that is there's only one density function like that. That is the uniform density. Sorry, not the this we are considering the cumulative distribution function here. That is the uniform cumulative distribution function. And if you take the density, you can say it's 1. That is the uniform density in the interval 0, 1. Right. So this is the cumulative distribution function of a uniform distribution in the interval 0, 1. If you take the density that is equal to 1, that is the density function of a uniform distribution in the interval 1, 0, 1. Therefore, you can deduce from that that y has a uniform distribution in the interval 0, 1. So that's a very useful and interesting result. If x is a continuous random variable with some CDF, and if we apply the transformation using that CDF for x, the new random variable y has a uniform distribution in the interval 0, 1. So we have now obtained the theory. Now I will show this, okay. I will demonstrate this by generating the distribution of f of x. Right? So let us suppose, for example, x has a exponential distribution. You know that exponential distribution is a positively skewed distribution. Let's consider an exponential distribution with rate parameter 2. Right? So it's a very skewed distribution. Now let's consider fxx, right? Transform x using the cumulative distribution function of x. And according to the theory, just the theorem or the example that we looked at a few minutes ago, it should have a uniform distribution. So let's see whether it actually, there is evidence for that. So for that, I have written down a small program, R program. I consider, first of all, I take 10,000 values from the exponential, 10,000 random numbers from the exponential distribution with rate parameter 2. Right? X equal to REXP, 10,000 values with rate parameter 2. Right? And then to calculate, get the cumulative distribution function of these values, cumulative distribution function of the exponential distribution, I say y is equal to PEXP. PEXP gives you the cumulative distribution function of the exponential distribution evaluated at these values. Right? PEXP evaluated at these values with rate parameter 2, of course. Right? So I have y values. So I'm going to show you the shapes of the density functions, of course, not the theoretical density functions, but the histograms we can look at side by side. So I want to get the side by side histograms. Therefore, I use this command pa mfro c 1 2. This will divide the graphic window into two columns, one row, two columns, right? So this is the command that you use for that purpose. If you want to divide the graphic window into two rows and two columns, then you say pa mf row c 2, 2. But here I want only one row, two columns. Therefore, I give this one. And then first, in the first part, it will have histogram of these x values, which are coming from exponential distribution. And then we will see whether the histogram of y looks like a uniform distribution in the 0, 1 interval. Theoretically, it should be uniform 0, 1. Right. So these are the two graphs. So you can see that this is the histogram of the 10,000 exponential random numbers with rate parameter 2. So you can see that's quite skewed, positively skewed. And this is uh, the histogram of y, which is equal to f of x evaluated at capital X. So you can see that it is not exactly a flat, of course, because it is a histogram, not the density function, but there is evidence that the distribution is uniform 0 to 1. Uh, another demonstration, I have looked at another example. Now, suppose X has a gamma distribution, again, a positively skewed distribution. In this case, I'm considering a gamma with shape parameter 2 and rate parameter zero point 0.01. So in this case, the mean will be equal to 2 divided by 0.01. So I'm going to again consider the cumulative distribution function of this gamma distribution evaluated at uh, x values. So let's say y is equal to f of x, and theoretically this should be uniform 0, 1. So we will again check whether whether there is evidence for that. So the commands for that, if I write down the program, only difference will be here. X is equal to r gamma, r gamma under this thing, and then 2 comma 0.01 r gamma instead of REXP. And then y will be P gamma X 2 comma 0.02. I have not shown those commands here. You can learn by yourself. Only difference will be those two. Instead of REXP, you will have R gamma, the same number, or you can increase if you want. Then 2 comma 0.01. The first one is the shape parameter, second one is the rate parameter. And then y will be the cumulative distribution function of the gamma distribution. So P gamma evaluated at these values, and then 2 comma 0.1. And then when you do that, this is the graph that I get again. Now, this distribution is the gamma distribution. Notice that the difference between the gamma and exponential. Exponential actually starts with some value here and then come down. The gamma distribution, of course, you know the density function usually starts with 0. So you can see that from this graph also start from 0 and then going up and coming down. So this is the gamma 2.01 distribution. And this is the distribution of y, which is equal to f of x evaluated at those x values coming from this distribution. So it's evident that again, the distribution of y is uniform 0, 1. Theoretically, of course, it's but here the histogram of 10,000 values come from a uniform distribution between 0 and 1. Right. I'm going to take a small break. Now, the remaining part will be recorded in another video. So this part is also very important and interesting. So we will look at that part in the next video.